All right, so in this video, we're going to talk about minimizing cost. Okay, so that is, we want the lowest cost combination of inputs for producing a given level of output Q bar. So that is, we're looking for the lowest possible ISO cost line. Remember, the lower you go, the less the cost. So the lowest possible ISO cost line that touches the ISO quant curve. Remember that means that touches, intersects, just shows us the combination for Q and cost that work together. Now, the reason why we're saying touches is because we want something that just touches the ISO quant line, not something that intersects it. Because if it intersects, then it means that we can even do better. So we're looking for the bundle, the L and K bundle, where ISO quant is, let's change color for this, tangent, that's what we mean by just touches, tangent to the ISO cost line. So if we were drawing this out, remember we have labor down here and cap. Okay, that's poor excuse for a line. Bear with me here. So we have labor down here and capital up here. We have three cost functions. Right, C bar 3, C bar 2, C bar 1, and we have an ISO quant Ooh, just touches it right there. That's nice. This is Q bar. So this is an ISO quant, right? ISO quant for Q bar. Let's highlight three interesting points here. We have this one, which is the one we like. We have this one, and then we have this one. This is just unachievable. So we have B, let's call that B. Let's call this A, and let's call this C. So there are certain things we should note about this graph. We have that the cost C bar 1 is greater than cost C bar 2, which is greater than the cost C bar 3. That is, C bar 3 is the lowest cost, right? Now, let's talk about points B and C. With point B and C, we use C bar 1 to produce Q bar, right? As we can see here, we can achieve a level of production at this point C. Same at this point B. However, they're not the best option, because at point A, we can use C bar 2, which is even cheaper, to produce Q bar. So therefore, we are going to, choose the L and K combo at point A, because it produces Q bar with a lower cost than B or C. Now, imagine if we had a point here. Let's call this D. D would be nice, but it is not achievable for producing Q bar. Okay, so from this, we can see that from the combination of all the stuff we just talked about, we can see that at point A, the isoquant is tangent to the ISO cost line. Isoquant curve. That is, when we have tangency here, we're saying that the slope of the isoquant is equal to the slope of, this is what tangency means, of the isoquant cost. Excuse me. If we were writing this out, we would say, remember, slope of isoquant is MRTS, marginal rate of technical substitution, where we have technical efficiency on the isoquant. That is equal to the slope of the isocost, which we derived earlier in an earlier video, which is negative W over R. Now, recall that MRTS is negative marginal product of labor over marginal product of capital. So we're setting that equal to negative W over R. This right here is the key finding, right? This is our cost minimizing. This is extremely important. Condition, cost minimizing condition. This is our cost minimizing condition. Okay, it's unfortunate that the color that I've used to show this extremely important thing is the same color that I wrote the example in, but we march on. Okay, so we've just derived and noted what our cost minimizing condition is, and we have an example. So in this example, we're given a production function. Right, this is our production function. We're given a production level of 50. Production function is important for MPL and MPK, right? Remember, MPL is the derivative of production function with respect to L. MPK is the derivative of the production function with respect to K. Okay, and we have W and R, everything we need here to answer this question. What is the cost minimizing combination? We can do this. Let's go ahead and do it. So first things first, we need to state that condition, right? We need negative MPL over MPK to be set equal to negative W over R. It's that point of tangency, right? This is okay, it's that point we want where we can go as low as possible with our cost. So to be able to do this, we just need to find MPL, find MPK, and then plug in 2 and 8 for W and R respectively. So let's get started. MP, let's rewrite this, Q is 5. Q is 5 times the square root of L and K. We can write this as 5 times L to the power of 0.5, K to the power of 0.5. Yeah. Yes. I can just hear my mind saying, how did you get there? So let's just answer that question very quickly. So as not to skip any steps, we have L and K to the power of 0.5. Right? The square root is just raised to the power of 1 over 2. Which is the same as 0.5. Okay, and we can distribute the 0.5 to each of these terms. So we have 5 times L to the power of 0.5, K to the power of 0.5. Wonderful. All right, so MPL here, let's do that first, be equal to dQ dL, which would be equal to derivative of 5 L to the power of 0.5, K to the power of 0.5 dL. So this would be equal to, we have 0.5 here, we'll bring it down and then subtract 1. We're just going to carry this like it's a number, just like we carried 5 through because K is let out. All right, so we end up with 5 times 0.5 times L to the power of negative 0.5 times K to the power of 0.5. That's MPL. So MPK is the derivative of this production function with respect to capital. So what is the marginal productivity of capital? How does capital change quantity? Okay, so we have D5 times L to the power of 0.5, K to the power of 0.5, dk. With this, we bring down the 0.5 rather, then subtract 1. We carry this L to the power of 0.5 the same way we carry the 5. Just keep it. So this will be equal to 5 times L to the power of 0.5 times 0.5 times K to the power of negative 0.5. Good so far? Okay. So I can rewrite this over here as 5 times 1 over 2, right? Because 0.5 is just 1 over 2, times L to the power of negative 0.5, K to the power of 0.5, which is 5 over 2 times L to the power of negative 0.5, K to the power of 0.5. Same here. 5 times 0.5, L to the power of 0.5, K to the power of negative 0.5, right? And we can rewrite this as 1 over 2. So this is 5 times 1 over 2, L to the power of 0.5, K to the power of negative 0.5. The reason we're doing this is because we have to combine MPL and MPK, and I want to write them in terms that will be as friendly as possible for us. So this is equal to 5 over 2 times L to the power of 0.5, K to the power of negative 0.5. So if this is MPK and here is MPL, we can combine these two. So we're looking for MPL over MPK. That is MPL divided by MPK. So this will be equal to, what's our MPL here? 5 over 2 times L to the power of negative 0.5, K to the power of 0.5 divided by 5 over 2 times L to the power of 0.5, K to the power of negative 0.5. Right. And we know that we can convert this division into multiplication. But let's carry on here. So MPL divided by MPK here will be equal to, I'm going to write these as square roots and put them in a fraction so that we can easily convert it when we convert the division. As in bring one over and the other one down. That's what I mean by convert. You'll see. Okay, so we have 5 over 2 times square root of K over the square root of L. Because this is negative, it goes to the denominator, divided by 5 over 2 the square root of L divided by the square root of K. Again, because this is negative, it goes to the denominator. So we can convert this to the multiplication sign. So this would be equal to the 5 over 2 times the square root of K over the square root of L times, what that means, convert it to multiplication, is that we're going to bring this to the top and take this down. So we end up with 2 over 5 square root of K over square root of L. Okay, with that multiplication sign, and then we can cross some stuff out. So with this, we can cross these out, cross this out, and then combine our K and L. So we have the square root of K times the square root of K over the square root of L times the square root of L. Remember, this is just K to the power of 0.5 times K to the power of 0.5 divided by L to the power of 0.5 times L to the power of 0.5. We're going through all of this math so that we can find our cost minimizing L and K. This is worth it for any firm. So at this point, we're still on the slope of isoquant. Our next here, we can just, since we have the same base, and we're multiplying, we're going to sum the powers. So this would be K to the power of 0.5 plus 0.5 over L to the power of 0.5 plus 0.5. This is going to be equal to K to the power of 1 over L to the power of 1. This is our negative MPL over MPK. Right? This is one portion of that condition. The second portion is setting it equal to negative W over R. So we have K over L is equal to negative W over R, and we know from the question that W is 2, R is 8. W is 2, R is 8. So we have that K over L is equal to negative, did we drop a negative somewhere? We did. This is all negative, right? The slope here of isoquant is negative MPL over MPK. So there should be a negative sign all the way through. Right? It showed up there. Stuff happens. It's good to have checks. This is one of my checks because both of them have negative, which is nice because then they get to cross out. So if only one side has negative, then I know that something is wrong. Where was I with my negatives? Okay. This is equal to negative. Perfect. So negative, and then we have 2 over 8. So we can continue the math here. Those negatives cross out. Right, it's a very great check. If you have a negative remaining, you know something went wrong somewhere. So K over L is equal to 2 over 8, which can be reduced to 1 over 4. So we have K is equal to, actually 4K, because if we take those, cross multiply, is equal to L. Or K is equal to 1 over 4L. Okay? Let's use this one. Now this is the first step, right? This is for any Q, but we want to nail this down for Q bar is equal to 50. Okay, so now we have to plug this. So plug this. Good one to know. K and L for Q. Plug this into the production function at Q bar is equal to 50. So we have that Q is equal to 5 square root of LK, but we have 50, so this would be 50 is equal to 5 times the square root of LK. Now, since we know what L is, remember L is equal to 4K, we can plug that in here. So we have 50 is equal to 5 times the square root of 4 times K times K. So we have 50 is equal to 5 times the square root of 4K squared. Now, we can apply the square root to each of these terms quite easily, where we would have 50, just going to do this on the side here. It's quite nice. So we would have 50 is equal to 5 times 2K, right? Because the square root of 4 is 2, and the square root of K times K is K. All right, and then we can solve for K as 50 divided by 10, which is 5. Now, we might not end up with a nice function or nice equation under the square root, so let's do it the longer way here. So we have 50 is equal to 5 divided by 4K squared. If we divide both sides by 5, we end up with 10 is equal to the square root of 4K squared. We're trying to isolate K. We're trying to solve for K, which is going to be our K star, our optimal cost minimizing level of K for to produce 50 units of goods or output. All right, so then we can take this square root to the other side. So this is 4k squared to the power of 1 over 2. So if you multiply both sides by, raise both sides to the power of 2, we'll have 10 squared is equal to 4k squared times 1 over 2, raised to the power of 1 over 2 times 2. Those cross out. So we're left with 100 is equal to 4 times k squared. Divide both sides by 4. So we can again isolate k. We have 25 is equal to k squared, which means that k, we're going to raise both sides to the power of 1 over 2, will be equal to 25 raised to the power of 1 over 2, which is 25, the square root of 25, which is just 5. Right, k star. This is a longer process here because we were trying to figure out what it will be if we didn't have such a nice function in there, where we could have just done 5 times 2k, which would be 50 is equal to 10k, and then k will just be equal to 50 over 10, which would be 5. Right, so much nicer there, but you might not always have such a nice scenario, so it's good to see the long graph too. All right, so we have that k star is equal to 5, which means that we can find L star. We know L is equal to 4 times k, so this will be 4 times k star, which will be 4 times 5, which in this case is 20. So the cost minimizing production or combination of L and K is 20 and 5. If we were to draw this out to visually represent this, we would need some information first. Let's find total cost of L is equal to 20 and K is equal to 5 to draw cost minimization point on a graph. We know that W is equal to 2 and K is, R is equal to 8, and we know cost, right, is equal to W times L plus R times K. So we have 2 times our L star of 20 plus 8 times our K star of 5. So that is 40 plus 40, which means our total cost here is 80. With this, we can figure out our intercepts for our ISO cost line. So let's start drawing that. K and L. If we spend all of our money on K, then an 80 of them, where all of our costs is 80, right? We just calculated that. Where the costs for each of them is 8, then we'll be able to get 10 units. So the max we can get of K is 10 if we decide to spend all of our costs on K. And then we can do this again for L, where we have 80 divided by, let's do this somewhere else. 80 divided by, what does that cost? $2. 2 is 40. So we have 40 there. And we can connect these two to get our ISO cost. Now, the only way we can say that this is the ISO cost is if it is tangent to our ISO quant line. So let's curve. So let's do that. So we have an ISO quant that is just tangent to the ISO cost line. So at this point, cost minimizing point, we have that L is equal to 20 and K is equal to 5. Ta-da. All right, if you have any questions about this, we kind of went through a lot of calculations, which is important, is something we needed to do to find that cost minimizing point for the firm. Right? It's something a firm needs to know if they're trying to maximize profit. How should we minimize cost? All right. If you have any questions about this, feel free to reach out. I will be more than happy to help you. My screen has frozen, so bear with me here. Okay. Good job watching this, by the way. I know it was a longer one. Good job.